admit it's not a very precise restatement of Euclid. Euclid is getting at something slightly different. It's a different cultural approach to what's really happening here. And now we come to the great Archimedes, who, just as in the parabola case, established really the benchmark computation for the circle. And this really is a benchmark computation, basically set the tone for circle area investigations for the next close to 2,000 years. So he wrote a treatise called Measurement of a Circle. These are his dates, 287 to 212 BC. And in this work, there's a subtle but important shift that takes place that we should make sure that we're aware of. Okay, there's a shift from areas to arc lengths. So here's a circle, and there's a radius r, and there's a circumference c, and also has an area. So we've seen the formula pi r squared for the area. But there's this other formula for the circumference. Circumference c is 2 pi r. So this is about areas, and this is about arc length. It's about the length, supposedly, of the boundary of the circle. Now, from our point of view of calculus, area is more fundamental than arc length. This is a more fundamental direction of a formula. And so Archimedes, he's really aiming at this formula here. He's aiming at calculating the circumference of a circle, say of radius 1. And if he does that, then he also establishes pi. So he can establish pi through this formula rather than through this formula. Now, there's a question as to whether these two pi's are really the same or not. Okay, so there's a theorem to be proven here that the constant of proportionality here and the constant of proportionality here are in fact exactly the same. That's actually a very subtle business that is finessed by almost all treatments of modern mathematics. It's a hugely delicate issue that really requires a very careful setup of Euclidean geometry to get it right and to be able to even do this. But from our point of view, it's not even possible to do this correctly because the pi's themselves represent quantities that we're not able to obtain. Okay, so I want to alert you to this dichotomy between areas and arc lengths. So nevertheless, Archimedes was interested in the arc length and trying to compute that and trying to estimate pi by a calculation of the circumference. And his strategy was the following. He says, let's start with a regular hexagon of side length 1, which is the same as the radius of our circle. So here's a circle of radius 1, and here's a hexagon. Now this hexagon is made of 6 equilateral triangles. That's an equilateral triangle. There's 6 of them altogether. And so if that side is 1, then that side is 1 as well. So each of these sides here is 1. So a crude estimate for the circumference of this circle is 6 times 1, because that's the circumference of this inscribed hexagon. That would be an underestimate, right? The actual circumference we should expect to be bigger than 6. Okay, so his strategy then is to do the following. We're going to replace the hexagon with a 12-sided figure. And we're going to do that by bisecting any one of these segments. So this thing here, we take a perpendicular to that other side. So in other words, we're bisecting that angle, if you like, and obtaining another point on the boundary, which is equidistant from the two that we already have. And then if we join these with line segments, then we get a 12-gon, a regular 12-gon, if we do the same thing all the way around. And then he's able to make a calculation. He's able to compute what this length is. Now, for us, lengths are problematic, but let's carry on with what Archimedes was thinking. So in his language, he's able to calculate the length of this thing as being the square root of 2 minus the square root of 3. That's a little bit subtle. And so, using that, he's able to estimate the new circumference, namely the circumference of the 12-gon, as being simply 12 times this. And since he's able to calculate square roots of 3, and then once he gets that, he can plug that into there, and he can calculate the square root of that thing, and multiply by 12, then he has a new estimate for 2 times pi. And then what he does is he carries on this way. So he knows how to go from one step to another. So the next step, he subdivides each of the given sides into 2. So he would split that into 2, creating a new point halfway in there, and then he would have a 24-gon, and then a 48-gon, and then by the time he gets up to a 96-gon, he has enough accuracy to get part of the estimate. He has a lower estimate. He can say that pi ends up being bigger than 3 over 10 to the 71. And involved in that are some quite heroic square root calculations. So this really does require facility with being able to calculate square roots to quite a few decimal places. And since the Greek arithmetic was quite, say, cumbersome, wasn't very accurate like the Babylonian arithmetic, this was quite a tour de force for Archimedes. But this is, to him, only half the story. Okay? Because what he wants to do is he wants to have an upper bound. He wants to sandwich this unknown pi between two things that he knows. Okay? So what he does is he augments this picture with another picture, which I'm not going to show you. So what he does is he takes, maybe I'll use a different color, maybe red. So he takes, let's say, the 6-gon to start off with. So just with the 6-gon, we have these 6 points here. He takes the tangents at each of these points. Let me do that a little bit accurately. So there's a tangent at that point there. And at the next point, which is this one here, there's also a tangent. Let's say that one. All right? Now these two tangents, which are adjacent, are meeting in a new point. Okay, so if you just think about this little quadrilateral here, formed from the center, the two original points of this new intersection of tangents, that's going to be a quadrilateral whose area is obviously bigger than the circular segment. And there's going to be 6 of those because we can repeat the thing 6 times around. So if he can calculate the area of this thing, he can multiply by 6, and then he has an upper bound for the area of the circle. That's a strategy. So whenever he does one of these subdivisions, then he has to augment not only the inscribed polygon, but also the circumscribed polygon. So the inscribed polygon is getting finer and finer with more and more sides, and so is the circumscribed one, and always his unknown value of pi is sandwiched between these two values. The two values are kind of getting closer and closer together like this, so eventually he gets them within a reasonably narrow range. And he concludes that pi is between 3 and 10 over 71, and 3 and 1/7. So this would be like 10 over 70. That's 10 over 71, a little bit smaller. In terms of decimals, this is 3.1408 and something. This is 3.1428 and something. The real value is 3.1415, at least approximately, which is somewhere in between there. This was the best approximation for quite a while. But moreover, it set a strategy. Okay, so it's a strategy for many subsequent calculators of pi. And what we should do is we should follow Archimedes and try to estimate the circle by essentially creating kind of splines. Right? We're creating splines, polygonal splines, based on regular polygons going around the circle, either inscribing it or circumscribing it. Now let's make careful note that Archimedes was not able to obtain an analog of his parabolic area theorem. What he surely wanted to find was a relation that allowed him to reasonably easily relate the area of a circular arc, let's say this arc, A, B, C, that portion of the circle cut out by that line, and the area of, say, the maximal triangle inscribed in it, say this one A, B, C, where this B is sort of the midpoint of the arc. That's what we have in the parabolic situation. In the parabolic situation, if this was a parabola, Archimedes would say the arc of the parabola is 4/3 the area of the circle. Wouldn't it be nice if there was some constant like 4/3, but some different value, that worked for the circle? But he was not able to find such a thing. In fact, he was not able to find any kind of easy relationship between these two areas. Okay, that's sort of the reality of it. The reality is that this fundamental difference between the calculation of Archimedes for the parabolic arcs and the calculation of Archimedes for the circular arcs, this separation is hugely important in the history and development of calculus and our theoretical understanding of it. Okay, so there's a gap. There's a separation that I want you to circle and the hyperbola. So here's the circle, and here's the hyperbola. We'll talk more about these things in a future video. So here's a piece of a circle, and here's a piece of a hyperbola. And the same problem does not have a precise answer either in the circle case or in the hyperbola case. We are not able to do what we're able to do over here. All that we can do over here is get approximate values. We can get intervals. You say, work hard and get there's an interval. The area of the segment, whatever it is somewhere inside there. And somebody else can work harder and get a smaller interval and say, I've got it now within a smaller interval. And then you can go away and work even more and more and more and more, and you get a smaller interval. But that's all that anybody ever can do. That's somehow the mathematical limit of what you're able to do. You're never able to actually get an exact value. Now, we pretend that we can. Yes, we have this elaborate real number fantasy story involving lots of letters and such, and symbolics that allow us to believe that we can get at these numbers, but the reality is that we can't. Okay? And it's important for us to look at this reality head on, not shy away from it, to really try to really come to grips with it. So this is very important, and it's going to be a theme that runs through the calculus. It's a very important theme for the algebraic calculus. Now, Archimedes' thinking was the forerunner of many other works in this direction. So this is a very central problem of trying to estimate the area of a circle of radius 1. And Zhu Chengxi, who lived from 429 to 501, a Chinese mathematician, used a 24,576 gon, which was 2 to the 13th, so taking the hexagon and dividing it up another 12 times. And he was able to obtain this beautiful estimate. Pi is roughly 355 over 113, and that's to decimal 3.1415929. And all the way up to there is actually agreeing with modern calculators. So it's very impressive. Al-Kashi, almost 1,000 years later, in 1424 in Samarkand, came up with this beautiful formula for 2 pi, 6.16.59.28.01.34.51.46.14.50.01. And that may look like a very kind of funny number, but that's a number in the Old Babylonian sexagesimal system. So that's with base 60. So it starts with 6, and then 16 over 60s, 59 over 60 squared, 28 over 60 cubed, etc. And it turns out, when converted to decimals, that it gives this value here, which is correct up to 6,4 there, and then it also gives these two values, but they're not in agreement with modern values. So our view is this one here, going up to 6,4 and then 7,6. And then we might mention, amongst many other people, more modern European mathematicians who have tried to calculate pi, L. von Ceylen, from the Netherlands, in 1610, spent a huge amount of his life calculating pi to what turned out to be 35 decimal places. And he used a polygon also with many sides. This was 2 to the 62 sides. So it's a very fine spline, okay, with 2 to the 62 sides, and he's computing probably circumferences, and was able to get pi to 35 decimal places. That took him many, many years. Since this is such an important calculation historically and theoretically, we want to also attempt to get at the area of a circle. But we're going to have a different point of view in 2 different ways. First of all, we're not going to assume that there is a well-defined notion of area. And we're going to take a more applied point of view, and maybe a less ambitious point of view, and restrict ourselves to the idea of trying to get approximate areas, very much along the lines of Archimedes. So we're going to find inscribed circular splines and circumscribed circular splines, but it's going to be different from most of the historical precedences in that we're not going to look for regularly spaced ones. So we're not going to think in terms of angles and subdividing angles. Rather, we're going to think about what's called a rational parametrization of the circle. So, but before we do that, we need to become a little bit more familiar with sums and some summation issues. And we also want to say a little bit something about tangents, because we need an understanding of tangents to get at the circumscribed. part of the integral calculus. And we're going to be interested in summing areas of polygonal regions first, and then summing areas of curved regions. So these formulas, the ones on this page, and generalizations are going to play an important role in that. The first formula is a very familiar one, I hope, that the sum of the numbers 1 plus 2 plus 3 all the way up to n is n times n plus 1 over 2. These are the triangular numbers, like 1, 3, 6, and 10. For example, if you add up 1 plus 2 plus 3 plus 4 plus 5, that's altogether 15, and that can be expressed as 5 times 6 over 2. Now, in this case, there's an easy geometrical explanation for that, because this sum can be represented by this region here, the red region, with the area of 1, 2, 3, 4, 5. And then if we juxtapose that with an equal region, the green one, with area 1 plus 2 plus 3 plus 4 plus 1, then they match up to form this rectangle of size n times n plus 1. In this case, 5 times 6. And that's why the individual sums are half of the product of n times n plus 1. Now, this important formula goes back to ancient Greek times, well known to Euclid. Then Archimedes discovered an extension of that formula to sums of squares of natural numbers. 1 squared plus 2 squared plus 3 squared all the way up to n squared is n times n plus 1 times 2n plus 1 over 6. And if you haven't seen this formula before, you might like to check it for some small values of n. Then a few hundred years later, Nicomachus discovered this formula for the sum of cubes. That 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed is n squared times n plus 1 squared over 4, which remarkably is exactly the square of this one. So if you want to add up the cubes, say from 1 cubed, 2 cubed, all the way up to, say, 10 cubed, that's exactly the square of the sum 1 plus 2 all the way up to 10. Beautiful formula. Okay, so these are important formulas for a wide variety of applications, but they're very, very important for calculus, both historically and conceptually. And what's really interesting is how to generalize these formulas for higher powers. That is, how do we go to powers of, say, 4, or 5th powers, or 6th powers, or more generally to kth powers? That's an important question that we're aiming towards answering. But before we do that, we should backtrack a little bit and just talk a little bit about summation notation, which is an important tool that allows us to deal with adding up things in a kind of an efficient way, especially when those things are arranged in a relatively organized fashion. So summation notation involves this Greek letter, this capital sigma. Sigma is like an S, and the S stands for sum. So the sum from I equals 1 to n of a sub I. What does that mean? Well, it means that we're supposing that we have some sequence a sub I, some objects, typically numbers, but maybe also polynomials or anything that we can add. And there's an a1, and there's an a2, and there's an a3, all the way up to some a sub n. And this means we're going to add up a sub 1 plus a sub 2 plus a sub 3, and so on, all the way up to a sub n. The sum from I equals 1 to n of the a sub I. So the index here, the I, is a kind of placeholder. It does not actually figure in the final result. It just allows us to keep track of what things are being added to get the total sum. So the bounds here, the numbers 1 to n, which bound the start of the sequence and the end of the sequence, should be natural numbers. And typically we want the first one to be less than or equal to the second one. But things are flexible, so sometimes we go from 1 to n, sometimes we might want to start from 0. A lot of counting is a little bit easier if you start with 0. Okay, so here are some examples just to show us how this works. The sum from I equals 1 to 3 of I cubed. When I is 1, we get 1 cubed. When I is 2, we get 2 cubed. When I is 3, the final one, we get 3 cubed. And the sum of those things is 36, as you can check. Here's an example where we use a different index rather than I. We don't have to use I. We can use j or k or in fact anything else. So the sum from j equals 2 to 5 of j minus 1. The j minus 1 is in brackets here, making sure that we're going to sum all of those things, not just the j's. So when j is 2, we're being told to compute 2 minus 1, which is 1, and add it to the sum. And then when j is 3, we get 3 minus 1, or 2. When j is 4, we get 3, and when j is 5, we get the last entry, which is 4. So this is another way of writing 1 plus 2 plus 3 plus 4, which is, of course, 10. Now, the bounds don't necessarily have to be specific natural numbers. They can also be variable natural numbers, in which case we don't get a number as an output, we get a polynomial typically, or some kind of expression involving that bound. So, for example, the sum from k equals 1 to n of k to the 5th. Now the bound is an n here, which is variable. We can change. We can even think of it as being a polynomial. Okay, so when k is 1, we have 1 to the 5th. When k is 2, we get 2 to the 5th, and then 3 to the 5th, 4 to the 5th, and so on, all the way up to n to the 5th, which is the final one, whatever n is. So this is just a way of writing this. It's really a polynomial in n of degree 5. Another important special kind of case is when we're just summing a constant. Let's sum from I equals 0 to 6, the number 1. Now, this 1 here does not have an I dependence. So that means that each time, as the counter ticks over from 0 up to 6, each time we're adding 1. That 1 is not changing. It doesn't have to change. So when I is 0, we have 1. When I is 1, we have 1. When I is 2, we have 1. When I is 3, we have 1. 4, we have 1. 5, we have 1. When I is 6, we have 1. So altogether, we have these 7 ones, and so the total is 7. So now we can re-express these sums of powers that we're interested in, and also to do some notation for them. So let's denote by S1 and n the sum 1 plus 2 plus 3 and so on all the way up to n. In summation notation, that's the sum from I equals 1 to n of I. Okay, the I itself is changing. When I is 1, there's 1. When I is 2, it's 2. That way we go through the sum. Now this particular sum, we know what it is. It's n times n plus 1 over 2. And then S2 then is the sum of the squares from 1 squared up to n squared. And here it is in summation notation. Summation I equals 1 to n of I squared. And we know what that is as a function of n. It's n times n plus 1 times 2n plus 1 over 6. And S3 then, the sum of the cubes. There's summation I equals 1 to n of I cubed. And there's the formula for that. And here then is the general formula that we're actually interested in. S sub k of n. So k is another natural number. And we're talking about the sum of all the k powers of natural numbers. Starting with 1 to the k, then 2 to the k, all the way up to n to the k, and adding them all up. In summation notation, here it is right here. Summation I equals 1 to n of I to the k. So I is the index, the dummy variable, if you like, that's running through our range from 1 to n. N is the limit, the final value, and the actual power that each one is being subjected to is k. It's I to the k. Now, our suspicion is that, following from the pattern here, this is probably a polynomial in n. In fact, it's a polynomial in n probably of degree k plus 1. This is quadratic, this is cubic, this is quartic. Seems to be almost one more than the power. And we'd like to know, what is that polynomial? How does that polynomial depend on k? K equals 4, what is it? K equals 5, what is it? K equals 6, what is it? K equals 100, what is it? So this summation notation is a very efficient way of dealing with adding up quantities. But there's some rules that we need to learn, and also some conventions that we need to be specific about. So the first rule is how to take the sum of two sequences. So supposing we have one sequence, A1, A2, A3, A4, etc., up to some value A sub n, say. And then another sequence, B sub 1, B sub 2, B sub 3, up to some value B sub n. And here on the left-hand side, we're talking about the sum from I equals 1 to n of AI plus BI. Okay, so that whole thing, when I is 1, is A1 plus B1. And then when I is 2, we have plus A2 plus B2. And then plus A3 plus B3. All the way up to plus AN plus BN. And what this rule is saying is, somewhat obviously, that this is the same as the sum of all the A's. The sum from I equals 1 to n of AI. Plus the sum from I equals 1 to n of BI. So it's a kind of an associativity with respect to this summation notation. A few remarks to make. Notice that we're not putting brackets around here. You might think that we should put brackets around here, but we're not going to, because we're going to adopt the convention that this sum extends, but doesn't include like a plus sign. Like that. So it extends up to there, but that plus sign means that now we're talking about something different. And that's also the reason why we had to put brackets around here, because if we didn't put brackets around here, then this would be interpreted simply as the sum I equals 1 to n of AI, that sum. Whenever that sum is finished, then plus BI, whatever that means. It would be then some ambiguous kind of thing. So we are obliged to put brackets around there. That's something that students often are forgetful of, so please keep that in mind. Similarly, there's a formula for the difference. Summation AI minus BI is the summation of AI minus the summation of BI. And then here's a distributive property, that if we're summing C times AI, and now C is just a number, a constant number, crucially, that does not depend on I. So it's the same, doesn't change. So what this really means is the sum starting with C times A1, and then add C times A2, add C times A3, all the way up to C times AN. And that comes back to C can be pulled out front, and the rule is telling us we're getting C times the sum I equals 1 to n of AI. Notice that in this case here, the summation is such that this product has precedence over the sum, so we calculate this product first. We don't have to put this in brackets. That's our agreement. And finally, in the special case, sum I equals 1 to n of 1 is equal to n. Alright, so there's no dependence on I. That just means that you have to add that same thing to itself as many times as the index runs over. In this case, there's n values, and so we get this number 1 added to itself altogether n times, for total n. So some simple but important rules that allow us to apply the summation notation to more complicated expressions. Now, before we get to the sums of powers that we're interested in, there's two other very fundamental and elementary kinds of theories that we want to investigate. And one of them is the arithmetic series. So let's start with the idea of arithmetic sequence. Sequences and series are different things in mathematics. A sequence means that you list a bunch of numbers or variables or some other things, one at a time, separated by commas. And there's no actual arithmetical operations involved. We're just listing things. So here's A1, A2,